Part G. There are 13 basic graphs that you'll need to be able to sketch very quickly without doing a whole lot of thinking. In a moment, we'll start looking at some graphical transformations, and we'll see how we can apply these to the 13 basic graphs. However, to be able to do those transformations, you need to, again, be able to very quickly sketch what these functions, and some of them aren't functions, look like. The first one, y equals x. Well, you know this. This is just a slanted line with a 45-degree angle that goes through the origin. We have points at 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3. Connect the dots. And we have our graph of y equals x. The domain of this function is all real numbers, and the range is all real numbers as well. Graph number 2, y equals the absolute value of x. Well, plug in some points here. Plug in 0, we get 0. Plug in 1, we get 1. Plug in 2, we get 2. Plug in 3, we get 3. Plug in some negatives. Absolute value of negative 1 is positive 1. Absolute value of negative 2 is positive 2. Absolute value of negative 3 is positive 3, and so on. Connect the points, and we get our absolute value V shape. The domain is still all real numbers. You're allowed to find the absolute value of any x value, but the range this time is just all the x values greater than or equal to 0. So I'll say my range is with a bracket 0, infinity with a parenthesis. Number 3, let's look at our standard parabola y equals x squared. Plotting some points, square 0, you get 0. 1 squared gives you 1. 2 squared gives you 4. 3 squared gives you 9. Negative 1 squared gives you positive 1. Negative 2 squared gives you positive 4. Negative 3 squared gives you positive 9. Connecting the dots, I get a parabola that looks like that. Number 4, y equals the square root of x. Well, square root of 0 is 0. Square root of 1 is 1. Square root of 2 isn't really a great value, so I'm going to skip that one. The next good x value we can plug in is 4. Square root of 4 is 2. Next good x value to plug in is 9. Square root of 9 is 3. And I get something like this. If I were to try plugging in negative numbers, square root of negative 1, well, that's imaginary, so that's not really going to work. I have everything that I need. Connecting the dots, we get half of a sideways parabola. My domain is with a bracket 0, infinity with a parenthesis, and my range is also 0, infinity. Number 5, x equals y squared. This is a little different. This is a function of y rather than a function of x. I think the best way to go with something like this is to try to make a table of values. My inputs this time are y values, my outputs are x values. If I input 0, 0 squared is 0. Input 1, 1 squared is 1. Input 2, 2 squared is 4. Input 3, 3 squared is 9. Putting some negatives in here, if you put in negative 1, you get out 1. Put in negative 2, you get out 4. Put in negative 3, you get out 9. To plot these points, remember that in my table I switched my x's and my y's, so these points are just 0, 0, 1, 1, 4, 2, 9, 3, 1, negative 1, 4, negative 2, and 9, negative 3. 0, 0, 1, 1, 4, 2, 9, 3. This is looking very similar to my square root function from the last problem. However, moving on, I have 1, negative 1, 4, negative 2, 9, negative 3. This is an entire sideways parabola, rather than just half of a sideways parabola. Notice that if I'm dealing with this as a function of x, well, it's not a function of x. It wouldn't pass the vertical line test. My domain here is with a bracket 0, infinity, and my range is all real numbers. This graph is exactly the inverse of the graph I had in number 3 of y equals x squared. The square root that I dealt with in number 4 is an inverse that was kind of restricted to make sure it was a function. This as is not a function. We're going to see that our graph in number 4, that square root graph, will be more useful to us than an entire sideways parabola moving forward through calculus. Number 6, I'd like to sketch y equals x to the third. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, so I'm not going to bother with that. That's off the graph. Negative 1 cubed is negative 1. Remember, when you cube a negative, you get a negative. Negative 2 cubed is negative 8. And connecting the dots, we get something like this. My standard cubic function. My domain is all real numbers, and my range is also all real numbers. Now I'm going to sketch the related root formula. Y equals the cube root of x. Cube root of 0 is 0, cube root of 1 is 1. I don't want to do the cube root of 2, it's a messy decimal, or 3, or 4. The next good value I'm going to find the cube root of is 8. Cube root of 8 gives you 2. We can do cube roots of negatives. The cube root of negative 1 is negative 1. The cube root of negative 8 is negative 2. Connecting the dots, I get a cube root function that looks like this, the inverse of what I had in number 6. My domain is negative infinity, comma infinity, and my range is the same. Both domain and range here were all real numbers. Number 8. Y equals 2. Well, that's just a horizontal line at a height of 2. My domain is all real numbers. And my range is actually just a single value, just 2. The way I'm going to show that in my interval notation is in brackets 2, comma 2. You're starting at 2, you're ending at 2, you're including 2. 2, comma 2, like that. Number 9, x equals 2. Well, that's just a vertical line. So x equals 2 will look like this. Not a function this time. It fails the vertical line test at x equals 2. My domain is just the single value 2, so I'm going to say the interval from 2 to 2. And my range is all real numbers. Number 10. Y equals 1 over x. Plug in 0. Well, actually, you can't plug in 0. 1 divided by 0, that's undefined. I'm going to hold on to that for a moment. Plug in 1. 1 over 1 is 1. 1 over 2 is 1/2. 1 over 3 is 1/3. 1 over 4 is 1/4. If I were to plug in some fractions, if I plugged in a half, 1 over 1/2 is the same as 1 times the reciprocal, so times 2 over 1, which just gives me 2. If I was to plug in a third, 1 over a third gives me 3. If I plug in a fourth, 1 over a fourth gives me 4. And again, we're not allowed to plug in 0. 1 over 0 is undefined. That's going to give me a vertical asymptote on my graph. Plugging in negative numbers. Negative 1 gives me negative 1. Negative 2 gives me negative 1/2. Negative 3 is negative 1/3. Negative 4 is negative 1/4. Plugging in some negative fractions, negative 1/2 gives me negative 2. Negative 1/3 gives me negative 3, and so on. And connecting the dots, I get a function that looks like this. We not only have a vertical asymptote, but we also have a horizontal asymptote on the x-axis. My domain is all real numbers except for x equals 0. So my domain is negative infinity, comma 0, union 0, comma infinity. My range is the same deal, all real numbers except for y equals 0. So I'm going to say again, negative infinity, comma 0, union 0, comma infinity. I also want to give equations for the asymptotes here. I have a vertical asymptote on the y-axis. The equation is x equals 0 for that vertical line. I have a horizontal asymptote on the x-axis, and the equation for the x-axis would just be y equals 0, the horizontal line at a height of 0. Number 11, y equals 1 over x squared. Plug in 0, and again we get a problem there. That will give us another vertical asymptote. Plug in 1, we get 1. Plug in 2, we get a fourth, so it's going down a little bit quicker. Plug in 3, we get a ninth. 4, we get 1/16, so we're getting closer to the x-axis faster. Plug in a half. 1 over 1/2 squared, well, that's 1 over 1/4. 1 over a fourth is like 1 times the reciprocal, so times 4 over 1, and you'll get 4. And the graph in the first quadrant looks something like this. Similar, just different steepness as to that last problem. If we plug in some negatives, though, it'll look a little different than that last problem. Plug in -1. 1 over -1 squared is positive 1. Plug in -2. 1 over -2 squared is positive 1/4, positive 1/9, 1/16. Continuing it the other direction, the graph will look like this. Both branches are pointing up. My domain is again all real numbers except for 0, so -infinity, 0, union 0, infinity. My range is everything above the x-axis. I have a horizontal asymptote on the x-axis, so I'm going to say 0, infinity. I have a vertical asymptote on that y-axis, x equals 0, and I have a horizontal asymptote on the x-axis at y equals 0. Number 12. I want to sketch x squared plus y squared equals 4. Well, hopefully you remember from pre-calc, this is just the formula for a circle. In particular, this is a circle with a center at the origin and with a radius of the square root of 4, so a radius of 2. I'm just going to graph 4 points and connect them to make a circle. My domain, in brackets, -2, positive 2, and my range is the same. Notice that this isn't a function. What's going to be more useful for us than things like number 12 are things in the form y equals the square root of 4 minus x squared. Well, this actually came from our formula for a circle. If I look at x squared plus y squared equals 4, and I do some work to solve this thing for y squared, well, subtract x squared from both sides. We get x squared equals 4, not x squared, y squared equals 4 minus x squared. Undo your square by doing the plus or minus square root, and the circle, just written in another form, is y equals plus or minus the square root of 4 minus x squared. In number 13, though, I don't care about the plus or minus part. I just want to sketch y equals the positive square root of 4 minus x squared. What that's going to give me is that same circle, but only the top half of it. It's going to give me a semicircle. My radius is still square root of 4. My radius is still 2, because again, notice the circle formula that it followed from. And my graph will look like this. We're going to deal with semicircles in here a lot more than we deal with entire circles, because semicircles are functions, whereas circles are not. D equals -2, 2 in brackets, and my range, 0, 2. If I change that 4 in the formula to some other number, like 9, my radius would then be 3. If I made that into a 25, my radius would then be 5. This is a semicircle in the form the square root of the radius squared minus x squared.